Okay, so let's just have a very quick recap. So we had three renormalization conditions. Two of them were associated with the Fourier transform of the two-point function. They told us that the residue of the pole must be I and that the pole must sit at the physical mass squared when p squared is equal to mp squared. The content of these two renormalization conditions is this statement that if you sum the line plus the line with a loop correction, you get this fat line, and the fat line is finite. It's just I over p squared minus mp squared. Then the equation for the coupling told us that if you take the amputated four-point functions, so the three diagrams that you see sitting here, the sum of those diagrams is the physical coupling times 4 factorial times by I. So notice that in both of these renormalization conditions, the left-hand side is a sum of terms, each of which has got divergent contributions. But the sum is finite and set by some parameters that we measure in experiment. So each individual term might be divergent. It may have epsilon dependence, m dependence, and g dependence. The sum of them is independent of epsilon and can be written only in terms of the physical coupling and the physical mass. We then said, well, if our theory is renormalizable using these three conditions, we should be able to prove that any correlation function to any loop order is finite. I told you that really the calculation is the same for any correlator that you want to study, and we looked at the four-point function. So we looked at the connected four-point function, and we've been working just to one loop. And there was only one point that was a little bit subtle, and it's the fact that when you're translating from the original quantities, mg and epsilon, to the physical mass and the physical coupling, there are certain terms that must be dropped because they're higher order in h bar, which means they're beyond beyond the one loop approximation. They're two loops and higher. And then we were able to show that when we summed these diagrams, we got an answer that was perfectly finite. It depended only on the physical mass and the physical coupling. So that's great. Now, I've really been making a meal out of these diagrams. So let me just try to stress, let me just draw the three diagrams here and just make sure that you know what I'm trying to draw so that you're sure of it. So the first diagram, if you look at this vertex sitting on the left-hand side, I've connected these two legs over here, okay? So you can see these are the two legs that connect to the one vertex, okay? So let's call this leg one. So focus on leg one. Here, leg one and leg two have connected, okay? Now, there's also a diagram where leg one and leg four connect, okay? So here is 1, 4, 2, and 3. So I fixed the outside ordering, and now it's 1 and 4 that connect. The last diagram, the one that has been giving me all of the trouble, what do we want? We'd like 1 to connect. And now which leg would we like to connect together with 1? We'd like it to be leg number 3, okay? So here 1 and 3 connect. And for this vertex over here, we would have 4 and 2 connecting, okay? So that's what I've been trying to draw. Maybe my skills at drawing diagrams are so poor that you weren't aware of that. I just wanted to make it clear. Now it is legs 1 and 3 that connected this vertex. And those are the three independent diagrams. Good. If you were dealing with some other theory that had, say, more than one coupling constant, maybe you had a quartic and a cubic vertex, then you would have one extra renormalization condition, and that would define your cubic coupling constant. In fact, you would have one renormalization condition for every coupling constant that you have, plus one telling you what is the physical mass, plus one related to the strength of the field. So what's the physical field strength? And that's related to the residue of the pole. But if your theory is renormalizable, then the claim is that using those renormalization conditions, that some finite number of equations, any correlation function to any loop order will be finite and expressible only in terms of the experimentally valued parameters that are defined by the matching conditions. Now, what you can see is, even though our theory depends on m and g, which are divergent quantities, and epsilon, which is going to 0, after we've done the computation, things only depend on the physical mass and the physical coupling. So the way that Feynman, Schwing, and Tominaga would describe this, they would say that the bare mass and the bare charge are infinite, but correlation functions, when they're evaluated, they give a finite answer. And this is all a very satisfactory state of affairs because the bare mass and the bare coupling are not observable. So no problem. In the next chapter, we'll have a much better point of view due to Wilson, which really says that there are no infinities in quantum field theory, and they'll tell us how to think about these divergences that we're seeing, okay? But we'll postpone that for now, and let's keep going with the Feynman, Schwing, and Tominaga claim. I hope from the example that we've checked that you would be able to go away now, pick some correlation function that you're interested in, and show that with our renormalization conditions, our 3 matching conditions, that it's finite. Okay, so that's a nice thing for you to practice. Good. Proving that the theory that all correlation functions to any loop order are finite is a tough mathematical exercise. It involves all sorts of combinatoric gymnastics and inventing nice notation. As far as physics goes, there's not much additional physics. You've seen the physics, so you just have to be mathematically a little bit patient and persistent. But one question that is good to ask, and in fact, it'll also be interesting in the Wilson point of view, is what is the set of renormalizable quantum field theories? So what is the set of renormalizable quantum field theories? Okay, and I'm sure you know, for example, that gravity is not renormalizable. So what's special about gravity compared to the other interactions? Can we make that clear? So equivalently, how do we tell? How do we tell if a quantum field theory is renormalizable? So how do we tell if from some finite set of renormalization conditions, matching conditions, if we remove all infinities from the theory? And in fact, there's a very powerful method to do that, and it's called power counting. So I'd like to discuss power counting now. Well, in fact, I want to just remind you of something first of all. So we use units in which h bar is equal to c is equal to 1. And in these units, after we've set h bar is equal to c is equal to 1, we actually only need one dimensional parameter. Let's take that to be length. So in these units, a mass would be an inverse length. I think you're familiar with this from earlier in the course. A momentum would be an inverse length. Let's study a regularization of the theory, which is a momentum cutoff. Okay, so we'll assume we're using a momentum cutoff. This is good enough for what we want to do now. Actually, more than good enough. It's very convenient for what we want to do now. So we are saying that P dot P must be less than or equal to some lambda squared. And of course, lambda has to be a length to the -1. Okay, let's study a couple of integrals, divergent integrals. Now, in fact, I'm just recalling results that you already know, so I'm just going to state them. I'm not going to rederive them. So I1, this is the first integral that we'll look at. This is, let's imagine it's an integral d4p over 2 pi to the 4. And then we've got I over p squared minus m squared plus I eta. Well, we've calculated this integral already. You know how to do it. So what would you do? You'd Wick rotate. After you've Wick rotated, you'd change from the 4 components of momentum to one magnitude of the momentum and 3 angles. The integral over the angles is trivial. The integrand doesn't depend on the angles. And we find that this will behave like lambda squared. Let's take a look at a second integral. We'll want to look at both of these examples. So here, let's imagine we've got an integral d4p over 2 pi to the 4. We've got I over e squared minus m squared plus I eta, and I over p plus k squared minus m squared plus I eta. And this one, it turns out, behaves like log lambda. Good idea for you to see if you can reproduce that, but I think that you will be able to, okay? And it won't come as a shock to you that these two integrals look familiar, because of course, these are precisely the integrals that appear in our matching conditions, okay? Now let's see if there's an easier way to get this lambda squared and this log lambda, okay? Well, we're just going to use dimensional analysis. So if we take d4p, what is d4p? Well, this is like length to the minus 4, because we get length to the minus 1 for each component of momentum. And then we've got all of these propagators sitting here, okay? And it doesn't matter whether I look at p squared minus m squared plus I eta, this would have exactly the same dimensions as I over p plus k squared minus m squared plus I eta. This is generally giving us the dimensions of a propagator, and this will have dimensions of length squared, because it's 1 over length to the minus 2, so this will be length squared. So if we look at the dimensions of I1, well, this looks like length to the minus 4 from the integration measure, length squared from the propagator, that's length to the minus 2. And if I want to write a quantity in terms of lambda that's length to the minus 2, I would say that this is lambda squared. Lambda is length to the minus 1. So what power of lambda gives us length to the minus 2? It's lambda squared. In the same way, if we look at I2, well, from the integral d4p, so let's maybe color code, okay? So this is the integral d4p, the integral d4p. That's what's giving us this length to the minus 4, okay? So here we'll have a length to the minus 4, and that's again coming from the d4p. And then from each propagator, we get a length squared, okay? So here we've got 2 propagators. So we will get a length squared times length squared. So length to the minus 4 times length squared is length to the naught, and length to the power of naught we think of as log lambda. If you had gotten an integral I whose dimensions was, okay, let's say dimensions. If you got an integral I whose dimensions was length to the minus n, then you would say that In is proportional to lambda to the n, okay? So what I'm telling you is you can estimate the divergence of any integral. So you can estimate how an integral diverges just by dimensional analysis, which is great. Dimensional analysis is nice and easy, and we understand that well. Well, this looks like a lovely claim. Well, lovely claims must have lovely evidence. So let's now ask why. Why is this true? And we'll turn to that in a minute.